So this second PowerPoint on modeling atoms, here we see a carbon nucleus. The second part is called atomic masses and isotopes, and it's going to focus on the question of what happens if you have atoms that have extra mass. So again, from page 100 in our textbook, we can imagine a sample of carbon. One form of carbon is diamond, and we can imagine that we pull out a single carbon atom from that diamond, and that carbon atom, like every other atom, well, it has a nucleus. And the nucleus consists of massive particles, the proton, the positive charge, 1 atomic mass unit, and the neutron, no charge, but also 1 atomic mass unit. In addition to those massive particles in the nucleus, we have a cloud of electrons arranged in shells, and they are outside the nucleus, a charge of -1, and a mass, many times it's so small that we can treat it as if it was 0. We'll talk about the electron's mass before this presentation is over. Now, if we look at the chemical elements arranged in the periodic table, we recognize that every one of these elements is a different type of atom. And we define an element as the simplest form of matter that has its own unique set of properties. So for example, for carbon, one of its unique properties is that it can form diamond. There is no other element that can form diamond, which is the hardest naturally occurring substance on planet Earth. So one type of thing we'll find in the periodic table, we'll find solids like silver. A lot of the elements are metals, which are superficially similar, shiny. But other elements like mercury are liquid at room temperature. And then on the right-hand side of the table, there are many elements that in everyday natural conditions are gases. And again, we can distinguish these elements on the fact that they have unique sets of properties, chemically and physically. Now, the elements themselves are listed in order of their appearance in the periodic table by the number of protons. The number of protons is specified by the atomic number. So for example, here, this carbon atom, we have an arrow pointing to the box for carbon, and carbon is the 6th atom that appears in the periodic table. Its atomic number is 6. It has 6 protons. If we added another proton somehow, if we could do that, the carbon would become nitrogen. If we added yet another proton, somehow, if we could do that, it would become oxygen. What I'm trying to suggest to you, though, is that under ordinary circumstances, the number of protons doesn't change. That's because the energy required to remove or add a proton to the nucleus is so great, it doesn't happen under ordinary circumstances. Again, different types of atoms appear in the periodic table, and an element is the simplest form of matter that has its own unique set of properties. Now, the number of protons is equal to the atomic number. That's always true. But in the special case of a neutral atom, if you know the number of protons, you also know the number of electrons. Why? Because the number of positively charged protons in the nucleus must equal the number of negatively charged electrons in the outer shells. Now, obviously, since protons and electrons are both elementary particles, they always come in whole numbers. And I've said this before, and I'll say it again, there's no such thing as 1/2 of a proton or 1.5 electrons. If you break a proton or electron into something smaller, it's not a proton or electron anymore. So that's why we say that they are elementary particles, and they always come in whole numbers. Less obviously, the properties that come with these particles are always coming essentially in whole numbers. For example, every proton always has the same mass. Every electron always has the same exact negative charge. You can't really distinguish two electrons on the basis of charge or distinguish two protons on the basis of mass. It can't be done. So we turn now to the topic of mass, and we want to recognize that we have a box here, and this box superficially looks like the boxes that appear in the periodic table. However, this is not a box in the periodic table. This is a means of talking about neutrons and protons, because neutrons, just like protons and electrons, they're also elementary particles. And these neutrons share the nucleus, and they share the property of mass with the protons. Here in the illustration, we see 10 pink circles with plus signs representing 10 protons, a 3, a 4, and a 3. That all adds up to 10. If we look also carefully at the unlabeled spheres, we have rows of 2, 4, 4, and 2, and there are actually 12 of them. So in this illustration, we have a nucleus of a particular element, neon, that has 10 protons, because every neon atom has a nucleus with 10 protons. That's what makes it neon. But it also has 12 protons, again shown as the blue-gray spheres. Now, what the box does is it uses nuclear notation. And nuclear notation can be thought of as a way of giving you a shorthand, a quick, down and dirty description of the masses and number of particles found in a given atom. So the number on top in front of the symbol is the mass number. And the mass number provides the total number of protons and neutrons in the nucleus. Whereas the number on the bottom is just like the atomic number that appears in the periodic table. And that's equal to the number of protons, and it identifies the element. If you've got 10 protons, you are neon. Less obviously, if we take the mass number on top and we subtract the atomic number on the bottom, then what the difference between those two numbers is the number of neutrons. So the numbers here ultimately represent atomic mass units. In a neon 22 nucleus, there are 22 atomic mass units, 10 protons, because of course it's neon, but also in addition to those 10, an additional 12 neutrons, making a total of 22 atomic mass units. And the numbers as they appear here, they're different than the grams which appear in the periodic table. So we don't want to confuse the atomic mass units of an individual atom or type of atom with the grams of matter in a sample of matter, which also appears in the periodic table. So again, real quickly, if we take this example with helium, the mass number is on top, and it's 4. The atomic number is 2. Every helium nucleus has 2 protons, and the difference between the two numbers, 4 minus 2, is the number of neutrons that are added to that nucleus to make it 4. So there you are, and that all makes sense, but here's the part that's not obvious. It turns out that both the periodic table and the metric system have been cleverly designed to complement each other so that we can take the atomic mass units in the nuclear notation and we can easily relate them to the grams of substance that we measure within an experiment. We can use often similar or identical numbers from the periodic table. Well, how does that work? To understand the idea of atomic mass, I draw your attention to the fact that we have a particular notation for a particular version of carbon. This is carbon 12, and again, this shows that it has exactly 12 atomic mass units. This is one form of carbon, the form that has 6 protons and 6 neutrons. Now, what is not obvious is that scientists have defined the atomic mass unit in terms of this particular kind of atom. In fact, they say it is 1/12 the mass of a carbon-12 atom, not any carbon atom, but specifically of carbon-12, which means that this one atomic mass unit is equal to the mass of a single proton or neutron, here shown as being about 1.67 times 10 to the negative 24th grams. So we have a relationship between the atomic mass unit and a very tiny number in grams. Now, if we tease that out, we just look at carbon. And again, there's that relationship. We notice something that's really very clever. If you have a mole, that large number, 6.02 times 10 to the 23rd, if you have a mole of carbon-12 atoms, well, that means you actually have 12 moles worth of atomic mass units. If a carbon-12 atom is defined as having 12 atomic mass units, and you've got a mole of carbon atoms, well, you've got 12 moles of those atomic mass units. And it turns out that the total mass in grams of those 12 moles of atomic mass units works out to being almost precisely 12 grams per mole. This is kind of convenient. Again, if we were to set it up as a problem to solve by cancellation, the carbon atoms would cancel, the atomic mass units would cancel, and we would simply have the number for the mole, 6.02 times 10 to the 23rd, times the number 12, because you have 12 atomic mass units in the carbon atom, and then you do that times the mass of a single proton or neutron, 1.67 times 10 to the negative 24th grams. And it turns out, if you do that, you get roughly 12.01 grams per mole. Now, it's not perfect because scientists are constantly tweaking their estimates of atomic mass based upon better data in different kinds of experiments. And so periodic tables sometimes have slightly different decimals to reflect the fact that the numbers for the tables are being tweaked. And that's what you want. You want scientists constantly testing and refining their ideas. You don't want them to say, oh, well, this is just true and never test it. So that's what we do. We keep testing the periodic tables. But even so, even though it's not an absolutely perfect one-to-one correspondence, it's so close most of the time that we can do the following trick. In practice, we can treat the atomic mass that's given for each element in the periodic table in two different ways. You can treat it either as the average number of atomic mass units for that particular element, or you can treat it as the mass in grams of 1 mole of that element. Again, the numbers are not in a perfect one-to-one correspondence, but they're awful close. So 12.011 atomic mass units or 12.01 grams per mole. That's very convenient, the way this has been set up for us to use. Now, why 12.011? Why not just 12? We'll get to that, but first let's acknowledge that in addition to the mass of the proton, the mass of the neutron, we have a third subatomic particle that we keep not talking about. And that is, of course, the mass of the electron. We've said before that we're going to treat it as 0, but we actually know that it's not 0. And we are talking about very tiny numbers here. And so the question naturally emerges, well, when do we care about the mass of the electron, or why don't we care about it right now? Why not? Well, let's look at that a little more carefully just to make sure we understand. An analogy is used in your textbook, and I think it's a pretty good analogy. You have a piano, and the piano is a musical instrument that has several keys, and the individual keys, there's 88 of them in a single piano, the individual keys are actually relatively light. They're made of a combination of wood and either a plastic or sometimes ivory as a coating, and they don't weigh much. The piano itself is very, very heavy. The larger part of the piano has a gigantic metal frame that's a combination of iron and brass, and it's got strings at high tension. It's surrounded by a heavily reinforced soundboard of wood, and so it's pretty massive. Pianos are hard to move, notoriously for that reason. Well, the mass of an individual key is nothing. It's negligible. You can ignore it compared to the mass of the whole piano. No one's going to say, hey, I'm moving a piano, and someone says, well, this piano has a couple extra keys. And no one's going to say, oh, it's got a couple extra keys. Well, forget it. It's too heavy, right? You wouldn't notice the difference if there were a couple extra keys. But even though the mass is insignificant, even though we don't care about the mass of an individual piano key when you're moving an entire piano, nevertheless, if you didn't have that key, if it was missing, the piano would be defective. It would not work. It would have one key that would not sound, that would not work when you're trying to use it to perform music. And so even though the mass of that key is insignificant compared to the total mass of the piano, every key of the piano is essential to that piano's function. So the electron is important, but its mass is so small we can ignore it. Now the mass that we can't ignore is the mass that's associated with the protons and the neutrons. That's why we have a special mass number, just to keep track of that. Each electron is essential to the properties of an atom, but it does not form a serious impact on the property of mass. We can put it that way. Now, the mass of the electron is said to be negligible, that you can neglect it compared with the mass of a proton or a neutron. But we can't neglect the masses of the protons and neutrons. And this creates an interesting situation, which is isotopes. As previously mentioned, we have versions of atoms that have extra mass. And so we have here 3 different isotopes of oxygen. You'll notice at the bottom, the nuclear notation appears. We have 16/8, 17/8, 18/8. And the number at the top, again, is the mass number with the total number of atomic masses in that oxygen. You'll notice also that each green cloudy area on the outside is labeled 8E-. That means they all have 8 electrons arranged in a certain way for an oxygen. And since every one of these is an oxygen, they're all going to have the same number of protons, the same number of pink circles with plus signs, all exactly the same, except for the neutrons. So here we have oxygen 16 with 8 protons and 8 neutrons and 8 electrons. All right, so since there's a total of 16 protons and neutrons in the nucleus, this is oxygen 16, 8 plus 8. If we add an extra neutron, we have 8 and 9, and so this becomes oxygen 17. But notice this does not affect the number of electrons in the outer shell. In the same way, we could add an additional neutron. We could have oxygen 18, 8 protons, 10 neutrons. But this doesn't affect the outer shell either. Not at all. Not at all. Because the masses in the nucleus don't affect the chemical properties of the atoms. The chemical properties of the atoms are based upon the arrangement of the electrons in the outer shells. In fact, that will form the next major discussion point in this course about how electrons are configured, how they're arranged around the nucleus, because the way the electrons are arranged is how things behave chemically. But the extra mass in the form of neutrons in these isotopes does affect the physical properties, and one physical property is measurement. If we don't account for the extra mass caused by some versions of oxygen having a little extra mass, any attempt to measure the mass of a sample of oxygen is problematic. We will not actually count every atom accurately. We will tend to overestimate the number of oxygen atoms are present because we're failing to account for the actual extra mass found in some oxygens. And so for accuracy's sake, in terms of measurement, even though the extra neutrons don't affect how oxygen behaves chemically, for accuracy's sake, we have to account for that extra mass. Now, some isotopes are very unstable and they're difficult to measure because they don't last very long. That's really true. But other isotopes are relatively stable and long-lived. And so Here we have pictures that compare some stable isotopes of 3 different elements. We have bromine in blue, chlorine in orange, and silicon in 28. Bromine in blue, you can see that most of the bromine, slightly more than half, is bromine 79. That's a version that has 35 protons because every bromine has 35 protons, but it has 44 neutrons, a little bit more than a one-to-one relationship, and the total mass number is 79, so we say bromine 79. Now, if every bromine atom was bromine 79, the atomic mass of bromine would be precisely 79. But as you can see, it's not. It's 79.904. That's because nearly half of a sample of bromine is another version of bromine, bromine 81, which instead of having 44 extra neutrons has 46. And that we account for those extra masses in our calculation for the atomic mass of the substance. Because in any sample of bromine, a certain percentage will be bromine 79, a certain percentage will be bromine 81. We can say similar things about chlorine. About 75% is chlorine 35, about 25% is chlorine 37. So instead of having an atomic mass of precisely 35, it's 35 plus something extra, 0.53, the decimal. With silicon, we have a more common situation, which is that almost all of the stable isotopes are one isotope, but we have tiny slivers, relatively small percentages, that have either 1 or 2 extra neutrons. And so instead of having silicon have an atomic mass of precisely 28, it's 28.086 to account for the tiny slivers of mass produced by other isotopes. Now, how to calculate those numbers? How do we get those decimals? Well, we take an idea called the abundance, and we multiply it by the number of atomic mass units. That sounds very straightforward. Well, in class, we first use an example from our textbook, page 107, where we talk about how teachers like to weigh their grades, how they stress some assignments more heavily than others when calculating a student's final score. So in this example, we have 3 types of assignments: homework, test, and labs. And we are going to first weight the assignments. 20% for homework, 50% for test, 30% for labs. Of course, that's a total 100%. And then we're going to take the scores that we actually get, the actual scores the students complete, and we're going to multiply them by those weights. 85 for homework, 75 for tests, 90 for labs, and then we just do the math. Now, when we do the math, it's important to remember that the percentage is treated like a decimal. So 20% becomes 0.2, 50% becomes 0.5, 30% becomes 0.3. When we do the math, 0.2 times 85, 17, 0.5 times 75 is 37.5, 0.3 times 9 is 27, and we add it all up. Our weighted score is 81.5. Okay, so that's an example from the textbook, and then we have just another, just for our curiosity. Suppose the numbers were different. Suppose these were the numbers. Well, then it would be 0.42 times 86, 0.25 times 54, 0.33 times 68, and we would add them all together, and whatever it said, that would be the final score. Now let's use the same kind of reasoning, only we're going to talk about the atomic mass of a sample of magnesium. And we're going to have, 3 isotopes: magnesium 24, magnesium 25, magnesium 26. And again, we're going to assign the percent abundance. We're going to say how much of each is present. Okay, so in a particular sample, 79% is magnesium 24, 10% magnesium 25, and 11% magnesium 26. Now, just like in the class average example, we'll take the masses times the percent abundance, and we'll get a contribution to the total mass. And when we get done calculating, well, then we will have an estimate for the total contribution to magnesium's mass from all the different isotopes. And again, what are we going to do with those percentages? Those percentages are going to be treated as decimals. So 79% becomes 0.79. So 0.79 times 24 is 19. 0.1 times 25 is 2.5, 0.11 times 26 is 2.9, and we add it all together. There's our estimate for the atomic mass of magnesium based upon these three separate isotopes. Can you do this problem? Well, we'll do an example which looks at isotopes of neon, one of the noble gases, and we'll identify three main isotopes: neon 20, 21, and 22, and then we have these percent abundances, and you would convert the percents into decimals. So 90.48% would become 0.9048, and 0.27% would become 0.0027, and 9.25% would become 0.0925. And you'd multiply them by the respective masses, and that would be your contribution, and that would be that. Okay, so this is a typical mass average problem, and it shows how we get those numbers in atomic masses. And the important thing is that you understand that the decimal that appears in an elements box in the periodic table, that decimal does double duty. One thing it does is it allows us to account for the actual masses of samples of elements. It allows us to account for the extra mass that comes in the form of neutrons. So instead of carbon having precisely 12, it's 12.011 grams per mole. And sometimes we can take that decimal, we treat it as the number of grams of a mole of a sample. And other times we treat it as the average number of atomic mass units found in elements of that nature. But either way, we can use that decimal for that purpose, because the periodic table and the metric system have been rigged so that the numbers you get are approximately the same, regardless of what you're trying to calculate. And that's kind of grand.